Well, hello, class. I wish obviously you guys were here and there was no pandemic or epidemic to be considered for health reasons. But, we're going to go with this online thing this week, and hopefully I see you guys next week just in time for AJ to make some more Caruso memes. That being said, we got to move on. So today, 12-1, tangent lines of circles. If you follow along in your textbooks, you should find it on page 762. Now, I can't yell at you guys to get off your phones, but I can already sense that some of you guys are already on your phones. I'd appreciate it if you were to put them away. Okay, thank you. I'm not going to name any names or anything. Okay, so first, let's talk about the idea of a tangent line. No, we're not talking about SOHCAHTOA anymore, even though I know you guys love and miss that. A tangent line is, let's say I have a circle. Well, convenient that I have a circle there. And a tangent line is just a line that, let's see what the official definition, it intersects the circle at exactly one point. So I can't draw a line that just cuts right through it because that would obviously intersect the front and the back intersected at 2 points. So let's say I have something right here, and let's see, I should grab a ruler here quick. Oh, there's one right there. A tangent line would look something like this. From my dead point, I would just intersect the circle at exactly one location. So here, this would be AB. We would say line AB is tangent to circle. Oh, I just need a center to find my circle. Circle up. And then since I said line AB, might as well throw on some arrows here. Okay, so it's all a tangent line is. It intersects the circle at exactly one point. Now, that may seem pretty simple, but it actually has a lot of interesting mathematical implications. So first, let's start off with everyone's favorite theorems. So, theorem 12-1 says that if line is tangent to a circle, then it forms a right angle with the circle. So we actually get a nice little perpendicular thing that happens right here. Is with the edge of the circle and our line, they're actually perpendicular to each other. And that actually matters quite a bit. So I'm just going to use the same, again, drawing for here. Just know that the line and circle are perpendicular if it's tangent. Okay. Example 1. Find angle measure. Okay. Now again, I'm going to probably go a little bit faster than I normally do for you guys, just because you guys can pause, rewind, and then obviously just send me an email if you have any questions. So first I'm going to need a circle, and I'm going to use one of my alternate frisbee. This is from college. My sister actually got this from me from Germany, so I might as well enjoy it for a circle mold. Not exactly what she was thinking, but what can you do? You guys know how great I am at drawing, so I figured this would be a little bit better. Now again, that's not the perfect circle. You gotta see here we move the disc a little bit, but it's as good as we're gonna be. So let's say I also have a point out here, and I need my ruler. Let's say I have my center So let's say I made that line, and let's see. Shoot. That line, and then I have here and here at the intersection. And I told you that this was 117 degrees, and this is x degrees. Is there any way I can calculate the value of x? Well, let's see, if I wipe away these little extra frays, all I've created is a four-sided shape. It's a quadrilateral, and just how all triangles have 180 degrees, all quadrilaterals have are 360 degrees, and we just said theorem 12-1 says that these are perpendicular. So those are essentially, 90 degrees. So x has to be 360, has to equal all four of those interior angles, 90 plus 117 plus x. So we can just add up all those together. Well, 90 plus 90 is 180, plus 117 is 180, plus 117 is 297. So subtract 297 from both sides, and x equals 63 degrees. So just by taking that one little concept of perpendicular, we can actually form all sorts of interesting hypotheses just from this. Now, x is further away, and I had steeper angles. My inside thing would have to compensate because my 90s aren't ever going to change. It's always going to be perpendicular along those edges. Okay. Let's see. I've also written down all my notes, so I apologize if I keep looking over here. Theorem. Well, might as well. Theorem 12-2. Let's see. Theorem 12-2 says that it's just the converse. So if line is perpendicular to a circle, then it is tangent. So all that is just the converse of theorem 12-1, where if P implies Q, converse Q implies P is also true. So it actually works both directions. If I have a circle, that wasn't actually half bad. And I know that this line is perpendicular. I know that this has to be tangent. I'm not going to intersect it again. There's no circle that I can draw a line through that's going to intersect it twice and still be perpendicular to the circle or the edge. Just isn't going to happen, just natural curvature of the circle. So theorem 12-2 is actually very interesting. It can only go one way, or it can go both ways, but it has to be true in both directions. Okay. Let's see. We're going to actually skip example 3, looks like in my notes, and jump right to example 3. Example 3, we are going to find a radius of the circle. Now again, I'm just going to use my alpha disc just to make it more consistent here. And it got even worse, actually, as it turns out. You can see my first arc was pretty solid, and my second arc left a little to be desired. Okay. But if I have some things going my way, let's see. If I have my center, I have my thing out here, I have a line that is tangent. And here, naturally, all I have is a right triangle. And my radius, remember, to center to my edge, so let's say my radius is x. This distance is still my radius, so it's still x. Let's say that this was 8, and that this was, how about 16? Again, these are both have to be x's because, again, my radius doesn't change. Center to the edge, those are both radii, so that would be equivalent. Now, whenever I have a right triangle, what can I always do for its distance or for its side lengths? Well, I can always do the Pythagorean theorem, which we've talked about quite a bit, where a squared plus b squared equals c squared. Well, if I know that, well, all I need to do is identify my hypotenuse, and that'll have to be c. So which one has to be my hypotenuse? Again, opposite the right angle, so here. Now the important thing is, 8 is not my side length, and x is not my side length, because x stops right here, and 8 only starts right there. So the entire hypotenuse is actually x plus 8. So I get x plus 8 squared. My b term, let's say it's x squared, and then I also get 16 squared. Well, 16 squared, I can just type that right into my CAL, see you later. So I get 256 plus x squared. Now the thing is, I'm going to need to do my x plus 8. Do not just say that that's x squared plus 8 squared, which is 64. Don't. It's the biggest algebraic mistake that comes up. It's one of the biggest, I should say, especially when polynomials are concerned. So remember that that means that this quantity is being multiplied, so it's x plus 8 times x plus 8. And we have to just distribute that. So I get x times x, so x squared. X times 8, so 8x. 8 times x, so 8x. And then 8 times 8, so 64. We should get 4 terms because we get a 2 by 2 multiplication where everything has to be multiplied by the other. And again, I get some common terms, so I actually get x squared plus 16x plus 64. And that has to equal 256 plus x squared. Now you may be saying, Mr. Lane, we haven't really gotten anywhere yet. That just seems like a whole bunch of mess, and doesn't seem like anything really worked out yet. And that's true, but if we do some algebra and just simplifying and combining like terms, we should be right there. So I got an x squared in both of them, so I can subtract x squared from both sides. Well, I can send my 64 over, so I get 256 minus 64. 256 minus 64, what I'm guessing 192, but I don't want to mess it up. 256 minus 64. 192 equals, and all I have left is that 16x. So you get x by itself, we can divide by 16, divide by 16. So our answer is x equals 12. So my radius in this case would be 12. And if you double check, 12 squared plus 16 squared equals 20 squared would be a good way of double checking that, again, with the Pythagorean theorem. You know what's funny? This would be the part where I say any questions or anything like that, but obviously you're a camera, so I can't do that. Really digging my my YouTube career so far. Okay, moving on. I think we got one more example, and we'll call it. Okay, so example 4 is this tangent? Question mark. So again, circle. You definitely see where I messed up, ran into my own hand. So let's see, I need more color. Numbers 26 and 24. out is this tangent. Well, again, to be tangent, tangent has to be perpendicular. And remember, perpendicular just means I have a right angle. If this was tangent, it would be a right triangle, so I can still use the idea of the Pythagorean theorem. So, if a squared plus b squared, does it equal c squared? Well, if it does, then it's a right triangle. In this case, again, c squared would potentially be 26. So I get 10 squared plus 24 squared, and then I also get 26 squared. So 10 squared, that's pretty easy, that's just going to be 100, but 24 squared is going to be 576. So I get 676. So if 26 squared is 676, then we should be fine. So 26 squared is 676. So the Pythagorean theorem holds up. A squared plus b squared does equal c squared. Therefore, it is tangent. So my answer would just be yes. Okay. That's all I have for you. Just continue to keep working on those homework assignments through Math Excel for School. If you have any questions, feel free to email me, and I hope I get to see you guys next week. Okay. Have a wonderful rest of your day.